The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and to get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Good morning from California. I am Francisque Savignan, the founder and CEO of EPARTRADE, and with me this morning is Judy King, the co-founder, and Brad Gilly, our wonderful host. So this is episode number 110 and 11 of Race Industry Now, presented by ARP. So we have a double feature, Judy, today, right?
Yes, we have another very strong double feature, two hardcore racing suppliers, both SCAT Enterprises, and immediately after will be Still Racing Products, SRP.
Excellent. I see Jack with us this morning, and we are getting a signal from a producer that we're going to bring Tom on. And so Brad, how are you doing?
I'm doing fantastic, Francis. Thank you very much.
So you're on for 2 hours today, right? You're going to be busy.
I know, I can't wait, but it's a lot of great things to talk about. And I have a feeling this 2 hours is going to fly by as they usually do. So.
Okay. Good morning.
Good morning. How are you? Good to see you, Tom.
Yes. Well, here we are again with another, episode with E-Trade, and we certainly appreciate being here with you, and hopefully we can share some insights into the topic of the day, which is crankshafts and engine blocks and things. And so with that, let's step off and get started.
All right, that sounds great. Well, thank you so much. Today's the theme of today's webinar is crank and rods and the relationship to short block assemblies. And joining us, Tom Lieb, the president of SCAT Enterprises, and also we have Jack McGinnis from World Products as well. And Tom, this is going to be a fascinating hour. I know it is, and really appreciate you guys coming back here for another Race Industry Now episode. First, let's just start talking about what our subject matter is going to be, and a little bit about SCAT Enterprises for people who don't know.
Well, the topic today is, the basis of an engine is the short block, and of course the short block compiles the block itself, and then you've got the crank and the rods and the pistons, and of course the interrelation with all that is what supports the black magic that the engine builders do with the cylinder heads and camshaft, valve train, injection, carburetors, exhaust system, et cetera, et cetera, et cetera. But without the support of the block and the crank assembly, the rest of it, horsepower, means nothing because it isn't going to last. So with that, years and years ago, I started the business when I was in college in 1962, and here we are today, almost 60 years later. And we've become, a prime player in the crank rod and rotating assembly business. SCAT has developed over the years to the point where we can make crankshafts out of castings, out of forgings, and out of billet. And our capacity is from roughly 10 inches long to 43 inches long. A 43-inch crankshaft would be, almost 10 inches in diameter, and that would be a 619 John Deere tractor crank that you see on, at the various events as far as tractor pull, and, the 5,000 horsepower or 6,000, whatever it is. And so we go from one extreme to the other. And of course, the crank business has to be aware of the block business, because the crank has to fit into the architecture of that block. And so the block people and the crank people have to be on the same page and talk to each other as the innovations come up. We have to support the block, and the block has to support us, and then both of us support the horsepower that the engine builders do. So with that, we can get started and talk about the various components and how they interact.
Yeah, well, and speaking of the block, Jack McGinnis from World Products is joining us here as well. So tell us a little bit about what you guys do. And then obviously we're talking about a relationship with the rotating assembly and the blocks and all of those other good things.
Yeah, well, World Products has been manufacturing cast iron engine blocks for 25 odd years now. And it, like Tom said, the block is really, you can have the best crank and rods in the world, but if the block isn't capable of supporting it in a stable fashion and keeping it in place and supplying proper lubrication, those other parts aren't going to survive either. So we've designed blocks that we pour all ours in a Schedule 40 iron, which is roughly twice the strength of the ultimate tensile strength of an OE style block. And then they have added material in critical places to provide extra support. 4-bolt splayed caps that anchor into the strongest part of the block in the pan rails, and then a priority main oiling system, which provides oil instead of the typical OE setup, which was designed to be easy to machine, and it would supply oil to the cam and lifters and then to the mains. We supply oil to the mains and then feed the top end, which always has enough oil anyway. So it's a symbiotic thing. Like the cranks and rods and the block have to work together, as Tom said, or the whole thing will fail. So that's our mission, is to provide blocks that will support those critical rotating parts and all the other components and survive in high horsepower, high stress applications.
All right, thank you for that, Jack. As always, I do want to remind anyone viewing, if you have a question for either Tom or for Jack, you can just type it down below into the chat, and we will get to as many of your questions as we can and get those answered as thoroughly as we can. So we are here for you. So please feel free to let us know everything that you've got going on. Well, Tom, let's talk about cranks and blocks and, different main sizes, common sizes, a Chevy 350, 283, 400 sizes. Ford's got a 302, a 351 Cleveland, 351 Windsor. Give us some advantages and disadvantages of all that.
Well, and it goes back to reliability and strength. If you go into the NASCAR area, of course, those classes are governed by a cubic inch limit. And of course, the engine builders have come up with various combinations. And one of the things that they're very concerned about is friction. So the diameter of the main is a critical item, along with the size of the rod bearing. And of course, the block has to be machined to accept all that. The biggest thing with any of this is understanding the strength of the block versus the strength of the crankshaft. And like Jack said, their blocks are cast out of absolute premium material. Well, the changing in the main size If we go smaller, it reduces friction, number one. Number two, of course, that adds material in the block, which makes the block that much more stable. But the flip-flop is that depending on what the stroke is, the overlap between the main and the throw is going to change. And the strength of the crankshaft is in two places. It's in the actual material and the heat treating itself and how the crank is machined and processed. That's one thing. And the other thing is the strength of the crankshaft. The only material that matters is the top of the main bearing, the radius at the top of the main bearing in relationship to the throw, to the bottom of the radius of the throw in the same plane. That little section on all four of the crank throws in a V8 crank, that's the only material that counts. The rest of it pretty much goes along for the ride. So when you add and subtract on the main bearing sizes, that strength of the crankshaft, as the longer stroke is used, if you go to a 410, sprint car engine as an example, you don't dare run a 283 main size or in a 4 to 302 bearing size, because the overlap goes away, and therefore the crank, as far as the strength of the crank, goes away in the process. So the block folks having the different main sizes available, of course, has to be combined with the actual engine build itself. And then the crank guys like us, we have to make the crank. And of course, our mission, along with the block folks, is to make the strongest and best part possible. And of course, through our experiences, this will give the information to the customer, and we can discuss it and make sure that everything is where it needs to be. But it's about strength and it's about friction. And the friction, if you're trying to get that last 5 horsepower, then friction becomes an issue. But when you get into the average street double purpose engine that might be in a street rod or a muscle car or something, that extra little bit of horsepower is not as valuable as keeping the engine together and making the whole assembly reliable. So that's basically, our mission is to juggle all of these different factors and to make the best possible part for the customer to meet his expectations.
I'm curious, Tom, as people are trying to find horsepower and do different things, obviously friction is a huge factor in this, but people are trying to save weight and do all kinds of different things. When you're talking about the compromise involved, there's reliability, but maybe if you could shed some weight or you could do some things here or there, you might end up potentially sacrificing some of that. Where is the most stress put on these parts? Is it in an engine that is constantly running at a high RPM? Is it one that's going back and forth, say a lap after lap thing on an oval track or a road course, or, say with a drag racing application, one that just literally just goes out there and hits the power, straight from the get-go and maintains it for a short time? Where is the most stress caused?
Well, the most stress is caused through rapid acceleration and deacceleration. So in a drag race application, the hardest thing that they put on the crankshaft is the burnout, because you launch it and off it goes, and then all of a sudden you put the brakes on. So you've got extreme acceleration and there's no shutdown area. So the whole thing stops. In a dirt track type car, whether it be a IMCA modified or a World of Outlaw sprint car, the biggest problem with that is that on the dirt, the good drivers know that the fastest way around the racetrack is up on the cushion. And, you head for the fence and you hope that you're only 6 inches off, because one way or the other, it could be a problem. And of course, what ends up happening again is that rapid acceleration and then the rapid deacceleration. In NASCAR, many times you've watched a race and you see somebody go down, especially like at Talladega or someplace like that, a real high speed joint with, a big, camber on the corners and stuff. Car goes into the corner, he's all alone, and all of a sudden he goes into a spin. Well, what happens is the driver takes his foot off the gas, and of course the chassis unloads, and then he goes for a ride. Well, that abrupt, again, acceleration and deacceleration is jerking on the crankshaft, And the back of the crank is held into place as far as rotation by the drivetrain and the tires on the racetrack. The front of the crankshaft, it's got all that momentum going, and there's nothing controlling it. So the crankshaft being a zigzag as you go through a main bearing up into the throw and back down to a main bearing and so forth, the front of the crank wants to keep going, and the back end of the crank says, we're stopping. And of course, that's when you get this twist, and that wiggles the material back and forth. And eventually, two things are going to happen if it gets out of hand. One of them is it'll jerk the main webs out of the block, or the crank will snap. And so it's that rapid acceleration and deacceleration and all types of racing have it. And it's controlled a lot of different ways, but that's where the damage is done.
Jack, when it comes to the block side of things, what are some things that we need to know in what Tom was just talking about?
Well, material, of course, plays a big role. Adding extra material in those areas that have to support all those stresses on the crankshaft. The fasteners that hold the main caps in place and the register of the main caps. We use a dual register, which is a stepped register on the end of the caps and then ring dowels on the fasteners, so that everything is held securely in place and there is as much strength as you can possibly put into those main webs, and supported by the pan rails and even the decks, all that material to try to keep things stable so that the crank doesn't have a chance to move in a way you don't want it to.
I like that. Oiling. And Tom or Jack, I don't know who is the best to actually take the question, but what does priority oiling on blocks and direct shot oiling on cranks mean?
Well, priority main oiling in a block means that the oil passages have been routed differently from the OE stuff. When they designed these engines originally, most of it was designed to be inexpensive to manufacture. And so the way that they would drill the oil passages would oil the camshaft and the lifters, and then from there it would send oil to the main bearings. And in an understressed passenger car engine that worked, but when you get into racing applications, there's a lot of built-in leakage, I guess you could say, in that top end stuff, and it can cause starvation to the main bearings. So what we do is drill the passages in such a way that the oil goes to the main bearings first and then feeds the cam and lifters in the top of the engine, so that you always have reliable lubrication to those main bearings, because that's what's really critical. The direct shot oiling is a similar concept, and Tom can speak to that better, I think.
Well, keep in mind that most engine failures is because of lack of lubrication. And the lubrication, of course, starts with the block and then gets to the crank. And the old saying, the shortest distance between 2 points is a straight line. And so when we talk straight shot oiling, if you go back into the various factory crankshafts that have been made over the years, there's various schemes as far as getting the oil from the mains to the rods. And of course, the end of the line as far as oil is concerned is the connecting rod. And of course, the connecting rod is where the most abuse happens, but it's at the end of the oiling system. So one of the things that we certainly appreciate from World is actually there's two things from the block standpoint, because it helps us as a crank manufacturer. The first thing is the way that they've anchored their main caps to the block with the studs and the hollow dowel pins and things. The other thing that they've done is their priority oiling. Now with that, what we've done is we've taken it from there, and we have basically it's a straight line from the main bearing up to the connecting rod. And when you look at some of the factory crankshafts over the years, they have cross drilling where they have a oil hole that runs straight through the journal and they intersect someplace in the middle with the oil hole that goes to the rod. Well, what happens is with a system like that, there's two things that go wrong with that. One is that as you pick up RPM, centrifugal force takes over. And of course, the oil, when you stop and think about it, 7,000 or 8,000 RPM, you know, it's I guess the only way to say it, it's unreasonable to think that oil all of a sudden is going to make a left-hand turn and go up to the rod from the main. Well, it doesn't do that. But we have some energy that we can take advantage of, which is centrifugal force. So if we feed the oil in right off the surface of the main bearing, we put a scoop on it so that it's you know, actually directing the oil into that hole. And from there, it overcomes centrifugal force on the center line and then gets up into the rod. The problem is that system fails when you get above about 9,500. And there's two failures that happen. One is that the oil pressure is not sufficient to overcome centrifugal force. And the other one is that if you increase the oil pressure, what ends up happening is, to overcome that, what ends up happening is the leakage then that happens because you're feeding too much volume, then that takes over and presents a problem. So what we do is, if the engine's going to run a much higher RPM, first thing we'll do is decrease the size of the oil hole. Now that's directly opposite of what normally people would think. You know, if you need more oil, make the hole bigger. But the thing is that you're talking about pressure and volume, and you're also talking about leakage. Now, the other thing that goes on with the cross drilling, and of course, World has taken care of this. We know that on a basic engine block, that at RPM, the main bearing cap holding the crankshaft, the main bearing cap will distort anywhere from 3 to 4 thousandths. So what happens is, if the main bearing is cross drilled, you basically pressurize oil into the main bearing cap, which goes down into the pan instead of to the rod. And eventually, obviously, you're going to lose the rod bearing. So that's why main bearings, if you look at it, they have a groove in the top and they don't have a groove on the cap side. Now, to get more oil, a lot of engine builders and some of the bearing suppliers have taken and put a semi groove in the cap. In other words, they extend the groove around a little bit to get more oil in there. That works, but it only works if you've got a block like a World block that has a stable main bearing cap. If you've got a block that doesn't, then you've just, you know, made the problem that much worse. One of the things, that way we discovered all this, actually the straight shot oil system, you know, the engineers that originally designed the 265 Chevy back in 1955, 54, when it first came out, they actually pioneered the straight shot oil system. And all of us crank guys, we all thought that we had a better idea. And so we experimented with a lot of different things, and only to the extent that we realized that we weren't as smart as those guys, that we should just follow what they did, because what they did was absolutely right. And so we still hang on to that today, and it works. And in a combination with the block and ourselves, why we can pretty much give the engine builder, you know, the reliability that he's looking for.
That's interesting. We have a question from the chat, and this involves the block. Are there any advantages to using ductile iron instead of gray iron for the block? Are there disadvantages of ductile iron? And we'll start there. There's a second part of the question that involves the crank as well. So Jack, do you want to take that first part?
Yeah, we use ductile iron for caps, but blocks are generally always some variety of gray iron. Now, there's a lot of leeway in what that means. You know, there are different alloys that have different strength characteristics, but the gray iron has the combination of tensile strength and elasticity that you need more, where the ductile is probably less elastic and works better for a cap, but the blocks are generally always a variety of gray, and that can be from the OE stuff, which is like a class 20. A lot of aftermarket stuff will use a class 30. We use a class 40. You get beyond that, and again, it becomes more brittle than is practical for the application. So generally, it's some variety of gray iron.
But when you start talking about class 20, 30, 40, what are the differences there? Is that just a strength rating, or what is that?
Yeah, it really is. Those are, I don't think it's a SAE classification, and it refers to the tensile strength primarily, but also the elastic modulus, and but it's a factor of the amount of nickel and other metals that are alloyed into the iron.
Okay. And then the other part of the question, and Tom, I'll throw this over to you, is for the crank. It says some production cranks are made from cast iron. Is this gray iron or ductile iron? Which cast iron is better for making a crankshaft?
All right, well, let me back up a bit. That's a good question. But I think as far as metal is concerned, not only with blocks, but with crankshafts, one of the things that we need to talk about, and I'll answer the question, but is the structure of the material as far as grain structure. And this is in crankshafts as well as the material that's used on blocks. A regular gray iron or a modification of gray iron, the actual structure of the grain is larger on a gray iron than it is on a ductile iron. And what the grain is the metal holding hands with each other. In other words, if you go out into the street and you look at asphalt and you see the stones in the asphalt, and this is maybe a hokey explanation, but it'll give you a barnyard idea of what's going on. The gray iron would have the consistency of asphalt, and the ductile iron would have the consistency of cement, which has just the small sand grain. And the ductile iron, and Jack mentioned the nickel and the chrome. Nickel and chrome is what makes a steel, whether it's cast or a forging or a billet. That's where the strength comes from. The actual ability for a material to be heat treated up to a structure that is necessary for whatever the use is put to. Nickel and chrome is that element that makes that happen. Now, the problem with that is nickel and chrome don't like each other. So when you go to heat treat, what happens is they have a tendency to separate. But that's the difference with ductile. The process with ductile is that they, through their heat treating processes and some other elements like vanadium that they add to the steel, that's what makes everybody hold hands. That's what creates the grain structure. And the refinement of the grain structure is what gives you the strength. Now, in a crankshaft, when it comes to a casting, you have the same thing. I mean, the gray iron or a derivative thereof has a broader grain structure than the other. And of course, the strength is based on holding hands. And if you have a smaller grain structure and more of it and more compact, then that crank is going to be stronger. Now, when you get into a forging or a billet, the most common question is asked, which is stronger, a billet or a forging? Well, in steel, first off, a forging or a piece of billet actually started life as a casting, and then it's rolled. It goes through a process of more compaction, and it develops the grain. And the grain would be like looking at a piece of oak as an example. Oak has that long grain and it's all connected from one end to the other. Well, you can imagine a crankshaft from the nose to the tail having that grain. In other words, it's holding hands from one end to the other versus a cast crank that doesn't have that type of structure, that has a grainy structure. And of course, that's why the tensile strength and more importantly, the fatigue life of the material is less with the casting because it isn't holding hands. And so when it gets to, a billet is always stronger because with the forging, and I don't have anything in front of me to demonstrate it, but if you take the grain and if you take a regular small block Chevy crankshaft as an example, the throw is approximately, well, it's 1/900 wide, so call it 2 inches. And so that grain on the billet, because the billet is forged into place. In other words, that throw originally was where the main bearing was, and it was pushed up into place. So what happens is that grain was 1/900 wide, and now all of a sudden you ask it to turn left, and if it's a 4-inch crank, it's going to go up 2 inches. It's going to turn right, go across 2 inches, turn right again, go down 2 inches, turn left, and go into the main. So you've taken this 1/900 grain and you've stretched it 3 times what it should have been. And it's kind of like a rubber band. You take a rubber band that's laying on the desk and it's there and it's all in one piece. And then you pick it up and you start to pull it. Well, what happens? It necks down, and then eventually it snaps. So with the billet crank, the cross section that we talked about, the top of the main to the bottom of the throw as far as the radius, that grain runs through there. So it's not interrupted. Where on a forging, that grain that goes through there has now been severed or stretched or pulled, and therefore it's not as strong. So as you go through the different materials from gray iron to ductile to a forging to a billet, it's all about the grain and how the grain was developed and how it was heat treated, which means that it went into a furnace. It was heated up, and then it was quenched, normally in glycol at about 1,050 degrees, and that shocks everything into place, and that's what gives you the strength of the crankshaft. And then the grain that remains is machined. And so you either machine it out of there or you leave it in there, and the strength, of course, develops from there. So you go from, again, gray iron to ductile to a forging to a billet, which is the strongest of them all.
Wow, that's a fascinating explanation. I love the examples as well. Some great way to illustrate all of that. All right, I know we talked a little bit about cross drilling, and if this is something that you already did cover, forgive me, but how does cross drilling affect the crank and the block?
Well, the cross drilling, as we talked about, it's about the use of it and the thought that oil will actually change, direction. And of course, it'll do that if it doesn't have any forces on it. But as you pick up RPM, it's not going to do that. Centrifugal force takes over. Oil is a mass. It takes time to move from point A to point B. And of course, when you're talking about milliseconds in the engine as the crank is rotating, as you're going 7,000, 8,000, 8,500 RPM, the oil is committed and it's going to go wherever the centrifugal force throws it. And of course, where you want it is at the rod bearing, but it's going to take the path of least resistance, and the cross drilling is going to take and pressurize the cap, which is going to leak into the pan. If you cross drill the throw, the problem with that is, and if you notice on a crankshaft, the entry of the oil into the rod bearing itself will be between 25 and 30 degrees before top dead center. And what's happening with that is we're introducing the oil into the bearing before it gets to top dead center, which is peak cylinder pressure when it lights off. And so we want that oil to be there. In days gone by, if you look at crankshafts that were first started to be oiled with pressure in the 1920s, they drilled the oil hole on top of the throw. Well, with modern engines, those engines had 4.5 to 1 compression. Today's engines, you put a turbo or some other artificial, air into the engine when it's running 2 or 3 atmospheres and so forth. Well, if it's at the top of the throw, that cylinder pressure comes down on top of the oil hole, and what happens? It blocks the oil off. So we found that 25 to 30 degrees before top dead center gives the oil pressure and an opportunity to lay that film of oil between the bearing and the crankshaft. If you cross drill it, again, what ends up happening is, first off, the cross drill, you're introducing the oil at 45 degrees before top dead center, which is too far away. The other thing is that when it rotates to peak cylinder pressure, you've got the bearing on top of the oil pressure entrance because you've got it cross drilled, and of course it shuts the oil off. So not a good idea. We used to make a lot of money, that with stock cranks back in the 60s. The first thing we did was cross drill it. We thought that was cool. We made $20 and the customer was happy. And then we found out that actually what happened, this was a project with Ford back in the early 80s when they went back into NASCAR. Ford was notorious for cross drilled crankshafts. And if you go to the old original crankshafts, that's something they just automatically did. But when Ford got back into NASCAR in the early 80s, and the engines, they first started out at 7,000 RPM, and then the whiz kids in the dyno room came up with more power. And as the RPM went up and the power went up, they started having a problem sumping in the pan. The normal circulation of a dry sump engine is anywhere from 13 to 15 gallons a minute amount of oil that's circulated in the engine. And of course, the dry sump has to pick that oil up and get it back to the tank and then start all over again. Well, what happened was as things started, going up the scale as far as RPM, the guys at Yates, they ended up with 20 and 25 gallons a minute. And of course, the dry sumps wouldn't pick it up. And of course, the engines filled up with oil and that became a problem. And so we finally figured out that, in fact, they had put transducers on the main caps to figure out that the main caps were distorting and they had leakage there. And then the idea of the entry of the oil into the crank, as far as the rod is concerned, that became an issue. We drilled the cranks to quote 1955 Chevy standards. Problem went away, went back to 13 gallons a minute. So, that's the history of it. And of course, all hot rodding is based on trial and error. I mean, we're not all whiz kids and we don't have these $30 million computers. It failed. We got to figure out how to fix it. And, the guys at World Products with their blocks and us on the other end with the crankshafts, this has been our life. And so what we're passing on to the customers is, quote, our life experience.
Well, it's a beauty and an art in all of that and figuring it out as well. I do want to remind you, if you have a question for either Tom or Jack, you can type it into the chat and we'll be more than happy to ask that. I know people have more curious questions than either what I have that's been prepared in front of me or what I have just on my own. So feel free to jump onto the chat and ask any questions you have. Next one up, what has World done with their blocks and SCAT done with their cranks and rods for clearancing on longer stroke crankshafts?
On the block end of it, we generally have cast in most of the clearance that's required so that the engine builder, his machining is minimal and he may have to dress things a bit depending on what rotating assembly he's using. But most of that we've cast in and then dressed with our machining so that, for example, our Ford small block, the Windsor style block, we cast in clearance for a 4250 stroke, which is about the maximum that you're going to stuff into that block. Depending on the deck height of the block, which block it is, we put in clearance for whatever the greatest realistic crankshaft that you'd be able to fit into that block with that deck height for your stack up. So the intent being to just make life easier for the engine builder to complete that assembly.
Tom, you want to jump in on that as well, as far as the cranks and rods for clearancing on longer stroke crankshafts?
Sure. And this is where the partnership between the block and the crank comes in. The longer strokes obviously cause internal clearance problems. And of course, with the blocks, there are raised cams that get the camshaft out of the way of the connecting rod as it rotates. That's one thing. But the real problem for us is as the stroke goes up, we have to cut the back side of the counterweight. We call it cam cutting of the counterweight. And we have to do that because as the rod comes down on top of the crankshaft, as the piston comes down on top of the crankshaft, on top of the counterweight at bottom dead center, as the stroke increases, that pulls the piston towards the center line, which means we have to remove material there. So depending on the deck height of the block, that'll allow us to run a longer connecting rod. And if we run a longer connecting rod, then we don't have to cut the crank back. When we cut the counterweight, that's when we end up with not enough counterweight. And the only way we can get it back is to put Mallory in it. And of course, that's something that costs money. Mallory is expensive. Mallory is basically tungsten. It weighs twice what steel does. So if we need weight to balance the crank, that piece of tungsten, we drill a hole, push the Mallory in. And of course, the first thing we have to do is replace the steel that we took out by drilling the hole, and then add the weight advantage of the tungsten, which is double. So if we take out 100 grams, a typical 1-inch piece of Mallory, the width of a counterweight it adds 100 grams to the counterweight. So that's one thing that we have to do. And if the block decks are increased, or depending on the Ford deck is of course taller than what a Chevy deck is, so we have more options there to run a longer connecting rod, which is a great help. And so the counterweight, from the balancing standpoint, we adjust that to the deck, and the guys that build the blocks, of course, have to build the blocks with a taller deck. The other thing is that on the connecting rods, the bolt is what gets into the camshaft. And so on the connecting rods, we use different length bolts, and we cut the connecting rod back to clear the cam where we can. And then, of course, that isn't always 100% fixed. So the next thing that happens is they run a smaller base circle on the camshaft, and that helps also. So the combination of the casting and the block, the length of the rod, and the camshafts, all of that stuff has to be coordinated. And that's where the partnership basically between the block guys, the crank guys, and the rest of the people that are involved, the piston people putting the wrist pins in the right place and things. All of these things have to be well thought out before a customer or an engine builder starts buying parts, because if he doesn't buy parts that are coordinated like that, he's going to get the engine all together, or he thinks he has it all together and the piston comes out the top, or he can't rotate it around 100%. So there's, the problem. Of course, that's too late at that point. So these are all important things to know before we get started.
Yeah, for sure. Another question from the chat here in regard to Tom's statement on grain flow on forging. At what point does a cast crank get close to a forged crank strength? Is it possible to use better iron and be almost equal to a forging?
As far as a casting being equal to the forging, that'll never happen. And it's because of grain structure. And what that actually is the fatigue factor. So an example where you take a piece of tin and you wiggle it back and forth and a crack starts, and then eventually it comes apart, that's fatigue. In other words, the crank wiggles in the block. The crank is hanging onto the connecting rod, and you've got reciprocating motion. In other words, the piston moving up and down and converting it into rotating motion. And of course, with the stroke, that leverage of the throw being out there is what takes the crank and moves it around. And it wiggles back and forth. And again, it's back to the radius on the top of the main to the radius on the bottom of the throw, that cross section. And depending on the stroke, that cross section is what prevents that from happening. With a cast crank, because it doesn't have grain that holds it together like a forging does, the grain is I'll call it sand, which is, I guess, an insult to the iron, but basically that's what it is in relationship to the longitudinal grain. So the forging and the casting will always be, the forging is always stronger, and it's because of the fatigue and it's also the impact, because on a forging, if you get into detonation and you really hammer it, it'll bend. With a casting, it'll stay strong, and then all of a sudden it'll just snap. And again, it's about the grain holding it together. So casting will never be as strong as a forging.
Fascinating. All right, here's another one. Pros and cons of one-piece versus two-piece rear seals on blocks and cranks?
Well, one of the things that the folks in Detroit did was to try to minimize the leakage in the back with a two-piece rear seal. And also the diameter of a two-piece seal is small in comparison to a one-piece, which actually locates on the outside diameter of the flange of the flywheel. The advantage of the rear seal being one piece is you can install it and fix a leak without taking the engine, the oil pan off and all of that if you happen to have a leak. But the other side of that is that the one piece rear seal, as RPM goes up, the surface speed on the seal itself increases. And because of the diameter, you can get into an area where that diameter exceeds the surface speed of the crank turning. Because of that diameter exceeds the capability of the seal to hold back the oil pressure leaking out. So that's why you'll find most race engines with a two-piece rear seal. Detroit did it to stop the oil leaks, but it wasn't a huge problem. But for them, a problem. I mean, if you have to take a car apart to fix it costs some money. It's easier to manufacture, and in the end, it's cheaper and easier to assemble. But from a race standpoint, the smaller diameter two-piece rear seal ensures that rear seal isn't going to leak on you as the RPM goes up.
Jack, did you want to expand on that? Do you have anything to comment on that?
No, he covered that pretty well. I think the two-piece seal, you may have to drop the pan, but the one-piece seal, usually you have to take the transmission out. So it's a either or in terms of difficulty, depending on if the engine's in the car or not. But either can work for their intended purpose.
All right. Well, thank you for that. All right. What are the advantages or disadvantages of a center thrust bearing, LS and Ford, versus a rear thrust bearing like SB Chevy?
Well, the crank wrap up, in other words, you start at the front and you start picking up horsepower. In other words, if you got a 400 horsepower engine, you got 100 horsepower, and then you got 200, and then 300, and then 400. If it's 1,000 horsepower engine, the multiplication is still the same. The problem with the big block Chevy and the small block Chevy having a rear thrust bearing is that the crank wrap up through the length of the block all ends up at the rear main. On the Fords, the Oldsmobiles, Pontiacs, Buicks, Chrysler, and now the LS, the center thrust cuts that wrap in half. And so from the crank standpoint, it helps the strength of the crankshaft because the thrust bearing, you've got two surfaces that hold the crank in place and prevent it from moving. You've got the vertical of the thrust surface itself, and then you've got the horizontal of the main bearing. And so if you cut it in half, then that means the wrap on the crank is going to be in half. And it's interesting that Chevrolet held on to that rear thrust, which is basically, as far as I can remember, the only engine that did, other than the Ford Flathead, but they stopped that in 1953. So, but and all the other engines use the center thrust. So with the redesign of the Chevy engine, putting the thrust in the center was a good move and kind of fell into into place. We lost the.
Interesting. All right. When it comes to, obviously engine builders, a lot of skilled people out there building engines. And, if I'm buying an engine, usually I'm going to trust my engine builder, but what are some questions I might want to ask, say, ahead of time? I'm not, especially if it comes to, I'm watching this and we're talking about, crankshafts and rods, and we're talking about blocks and all of that. What are some things that I may want to ask ahead of time, based on, or tell them ahead of time, based on my application or whatever I'm wanting to get out of it?
Yeah.
Well, the real intended use of the engine is a very important starting point. If it's going to be an all-out race engine or a street strip engine, mostly street, mostly strip, circle track. Those are all going to determine what many of the parts are and how they're implemented. And the power levels and the stresses are going to determine how much money you really should be spending for the components. What level you need to be at. So that's a real primary thing, I think. And then what your budget is, where you can be realistically in terms of where you need to be or should be. And then you get real specific, Tom.
Tom, I mean, obviously, if people are coming to SCAT and looking for what you have to offer, what are some questions they need to have?
Well, and I 100% agree with Jack. The first thing we have to do is determine and define the customer's expectations. The second thing is to figure out his budget and whether his budget will fit into it. Now, one of the things that we've done at SCAT is that we're probably one of the only suppliers that actually offer every niche of the market. In other words, we have cast cranks, we have a corresponding connecting rod that would match a cast crank. We've gone to all the piston manufacturers and determined which was the best piston for a budget engine. And we put all that together so that a customer doesn't buy an expensive H-beam connecting rod to put on a cast crank because it's a waste of money. The cast crank will never perform what the H-beam rod will perform at. So it's a waste of time and money. So the expectation and the budget is the first thing. As far as and that's from our point of view. In other words, when our salespeople, our technical people are talking to a customer, is to find out what that expectation is and then guide them to the proper parts. If a customer is out just shopping for parts, I think one of the biggest things that is important is for the customer to be aware of who the name manufacturers are. And if you're buying an engine from XYZ company and they tell the customer that it's not a world block, or it's a block, or it's a crankshaft. If they're buying an engine and spending their money, they should be aware of who the people are that are the leaders in the industry, that have spent the time and the energy and the effort to produce a part that would have integrity. And when it's no name, you have no idea where it came from. And in today's world, it's easy enough to, a part is a part is a part. And if it looks like one, it should be one. Well, that isn't necessarily the case. But you can rely on the manufacturers that are out there that are the mainstay of the industry and the engine builders. And it's interesting when you look at the advertisements in the magazines and on the internet and so forth. There are Jack's customers at World and our customers that are proud to advertise that they're using a World block and SCAT crank and rods and things, and they take advantage of our expertise and the efforts that we put in all of these years to produce and to design and develop these various parts, and we're passing it on to them. And the no-name guys, that when they copy things, they always miss the fine point. And they get 90%, but that extra 10% is when you get the dustpan and the broom when you've had a mishap. So it's knowledge is key, and it's from a manufacturer standpoint. We try to make the people as much aware of why we do things, why we did things. It's like we explained cross drilling as an example. There's a reason why we've done things, and Jack has explained about the priority oiling and why they did that. And that comes with experience. And guys that just copy parts, they haven't banged their thumbs and experimented and worked these things out. And I think the name brand people are where they've got to be.
Yeah. Spend wisely or spend a lot. That's it. You don't want to spend twice. Here's Jack. This is one for you. It says, I'm going to build a better than 400 horsepower 302 Ford. World has many different blocks. Is there any reason why one would be better than the others? I'm looking at the 4.125 bore.
Well, you're talking a 302 block, so that's an 8.2 deck. You get a couple of bore options and a couple of main cap options with that. If you're going 400 plus, I assume you're nearer to 400 than you are to 600 or 700. So the block with the nodular ductile caps and the ARP bolts, as opposed to studs, would be perfectly suited to your purposes in that case, I think.
Okay. Thank you for that. I know we're getting a little close on time, so I want to make sure that we've got everything covered that you guys want to. Tom, is there anything that maybe we missed here? Is there anything that you want to let the folks who are tuned in right now know about?
Well, we've covered a lot, you know, with the bottom end, and I think the one thing that besides getting the parts and having them compatible with each other, the final thing would be balancing and the difference between external and internal balance. And this gets into the block side of it. Originally, when you look at the 400 Chevy and the 454 Chevy, 302 Fords, these are all external engines, external balance, meaning that the crankshaft does not have enough space on the inside of the block. The architecture of the block is such that the crank guys, namely us, we can't put enough counterweight onto the crankshaft. So what happens is they put a counterweight in the dampener and they put a counterweight on the flywheel to make up for it. And this is just the way the stock engine is built. And of course, we take and on the block side, with World giving us more clearance on the inside, we can put more counterweight on the inside. And then by taking the components, making them as light as possible, using longer connecting rods so that we can maintain the counterweight diameter. And in some cases, we have to use a couple pieces of Mallory. But the balancing of it, this is where the block and the crank compatibility comes in. And the ideal situation is to sit internally so that you have your main bearings are supporting on each side of the throw, which is where you're balancing your counterweight is. And by the main bearings supporting it, the wiggle in the crankshaft, you don't have on the nose of the crankshaft, you don't have that balancer out there with this weight off center taking and literally just yanking on the crank like that. And what happens is folks, you know, go with the external balance and they don't realize that there's a thing called crack the whip, which means the faster you go, the more that weight multiplies. And as that multiplies, that means that wiggle goes from here to here. And that we talked about the fatigue life of the crankshaft. Well, the fatigue life of the crankshaft with the crankshaft wiggling automatically transfers into the block because the block is hanging on to it. So that takes and makes everything, you know, it could go real ugly real quick. And so that's one of the things to take in mind and keep in mind is that internal is the best. And, you know, that's from the reliability standpoint, that's where they want to take a look and make sure that they do that.
Well, Tom, Jack, thank you so much. Every time, you know, hear from you, it's there's something learned for sure, but we really appreciate you guys being a part of this here today. And I know a lot of folks learned it. And I do want to remind people, if you want to find out more about SCAT or about World Products, then you could just go to EPARTRADE and go to their individual pages and link directly to them as well. Thank you, gentlemen.
Registering on EPARTRADE is easy. Fill out your name, email, phone number, and create a secure password. Next, select your business type. Choose supplier if you're looking to display products or services and connect with buyers. Choose racing business if you're looking to find new parts and connect with suppliers. Choose race team if you own or are a member of a professional racing team. Begin typing your company name. We most likely already have your company in our database, which you can select from the drop-down. Then, enter your job title. Choose Claim Company if you'll be editing your company profile. Other members of your company can choose Join Company if they'd like to use EPARTRADE as well. You can view and agree to our terms of use here. If you'd like to receive our weekly newsletter, choose Accept. Click Register Now, and your registration will be submitted for approval. You'll need to confirm your email once it goes through. To keep our platform industry only, you'll be approved shortly after. If we require additional proof of business, we'll reach out. Welcome to EPARTRADE.